Hello there, this is exercise 5C. We're split into two parts. One of them is basically trying to understand what transformations look like, how to describe them, and a variety of other things with it. The second one is looking particularly at graphs which are unusual graphs. So I call them pre-drawn graphs, which make it a little bit harder because we can't use a bit of our knowledge of the functions themselves. But anyway, let's crack on. So first of all, you can see on this slide that certain things are happening to what is effectively the y equals x squared graph. The black one in each case, here and here, is meant to be y equals x squared. And I suppose the question is, what would make this yellow graph? What would I have to do to the basic y equals x squared graph to make it all the way up there? Now, the posh name for that is a translation, a movement upwards is a translation. And, I'm making up a number, but something like y equals x squared plus 5 will do the job nicely. That will cross at 5 rather than what it normally does at the origin. Sometimes, we want to do other things to them. For instance, this one here, this seems to be a reflection of the black line of some description, maybe even a stretch of it as well. But one thing you should be aware of, that's y equals minus x squared, this upside down one. And notice this one here has been really quite weird, the way that has been moved. It's kind of moved down and right. And this, for instance, I'm going to make up a point there. I'm going to say that is 2 across and 1 down. So this has an equation as well. So now I've made that number up, and it is made up because I don't really know what it is. But it would be y equals x minus 2 all squared minus 1. So it's interesting that those numbers there from this vertex, this turning point, and then being used in the equation itself. You can see they're very similar. Interestingly, it doesn't say y equals x plus 2 all squared. It says y equals x minus 2 all squared. And these are stretches from the original one. This grey one now has been shown as y equals x squared. And this might be, for instance, y equals 2x squared. It's a stretch parallel to the y-axis. So all of these things are what we meant to know from GCSE, but we're certainly going to make sure you did it properly. We are interested in 3 types of transformations. Number 1, a translation. Lots of people say it's moved up, down, left, right. Some people might say it's slid across the graph. But we are going to call it, this posh word is translation. And we need to know what a translation equation will look like, or expression. Second one is a stretch. Now a stretch is a one-dimensional enlargement, if you like. It pulls in one direction, maybe in the x-axis, but not in the y. Or I might pull it in the y, but not in the x. So it's a one-way enlargement, if you prefer. But it's getting bigger in one direction. And the third and final one that we have to be able to do for now is the reflection. So there are 2 types basically we're interested in: reflection in the x-axis and reflection in the y-axis. So here then is our first example, and what I want to do is just make sure that we can do these. And we're going to start with translations. There are 2 types of translation. Now you'll notice I've written this in terms of, I've said y equals f of x plus a. Now this is because very often in the exams they'll say y equals some function of x. And we're meant to either know what its graph looks like, or they'll draw it for us if they think that we're not meant to know what it looks like. Very often it'll be a simple graph. It might be y equals x squared, or it might be y equals x cubed, or even some really nasty ones we haven't even seen yet, like y equals sine x. You saw those at GCSE, I know. So you get a basic graph given to you, and then something is either added or subtracted from it. So I've written here f of x as a added to it, but it can be a takeaway. So describe the transformation that changes y equals x squared graph to the y equals x squared minus 2 graph. So this one is a takeaway, but it could easily have said plus 2, wouldn't have really mattered. And what you're meant to know is, first of all, what the x squared graph looks like. You're meant to know it does this. That's the x squared graph. And what you're meant to then say is, well, if I put a minus 2 on the end, it's no great shakes to say, well, it moves 2 down. Now the posh way of describing that, and these are the graphs, by the way. There's the original one, and there's the new one, y equals x squared minus 2. Y equals x squared minus 2. And notice it crosses at minus 2 on the y-axis. So how do we describe it? Well, we basically say it's a translation. And we have to say it moves 2 down. The easiest way to do that is to talk about the vector. So I've written the translation by the vector 0, minus 2. And you should know that this first number in the vector is a cross. I'm trying to work out how to spell a cross now. Is it double C? Who cares? And this means down because it's negative. So basically, 0 across. If it was positive, it would go right. If it was negative, it would go left. This says 2 down because it says minus 2. If it said plus 2, it would go 2 up. So there's our first one. So we will get examples like that. Second one. Notice now this is very similar. We get a y equals fx graph drawn for us, or we're meant to know what it looks like. And now it says y equals f of x plus a. Now that, look at the subtle difference. This one says f of x and then outside the brackets plus a. This one has a plus a inside the bracket. Now, when it's inside the bracket, you need to know something. It will make it translate still, because we're adding on, and whenever we're adding or subtracting, it will translate. But notice, this will not now move up and down. This will translate the graph left and right. So, very important that you suss. When it's in the brackets, it's going to do things to it left and right. And weirdly, when it's in the bracket, it will kind of does the wrong thing. And I always just explain that, because on the face of it, you know, f of x plus a, you'd think the plus would move it to the right. Turns out it doesn't. Turns out it moves it the other direction. So anyway, let's have a look at this question. Describe the transformation that changes. Well, this is not a very nice graph. This is quite a complicated graph. So I'm surprised it's so complicated. But let's do it anyway. Y equals 5x squared plus 2x minus 1. Now this would be a graph that you wouldn't really be expected to know what it looks like. And it says it changes it into a y equals, notice it looks really horrific, but really all that's happened is wherever it says x here it says 2x, here it says 2x minus 1. So we've replaced the x with an x minus 1, and we've done the same here. It says x squared here, but here it, rather than saying x squared, it says x minus 1 squared. So the very first thing you need to know is x has been replaced by x minus 1. And whenever you just basically completely take out one letter and replace it by a different expression, in this case x minus 1, then you need to look what you've replaced it by. Here replaced it by x minus 1. So if that's the case, you can think of this as one of these. You can basically say to yourself, well, I started with y equals f of x. I've allowed it to become y equals f of x minus 1. I've replaced the x with an x minus 1. What's it do? It translates it. And notice, let's look at these graphs. First of all, I have no idea what this looks like. It's basically a U-shape, slightly to the left and slightly down. Let's draw the graph. So this is the original one. This is this graph. Okay. And the blue one is my new one, the one I want to draw. Now, what has happened to it? Well, if you just look at it for a moment, it's basically the same graph, isn't it? It just seems to have moved over. It's moved one to the right. So this is what this does. I did say to you, when you get this thing happening in brackets, the x has been replaced by x minus 1, then basically it moves left and right. It translates left and right. And therefore, in this case, because it was minus 1, that makes it move 1 to the right. Notice, minus 1 would make you think it goes left, but in actual fact it always does the wrong thing in the bracket. So it moves 1 to the right. Notice what I've written, that x has been replaced by x minus 1. You didn't need that, that's just me telling you that. And therefore it's a translation. This is what you get the marks for, by the vector 1, 0. 1 meaning 1 to the right, none down or up. Next one. Right, so this now is y equals a f of x. A f of x. So what does that mean? Well, for instance, I might have y equals x squared, and my new one would be y equals 5x squared. Notice I've times what I had by a number. And this is best described as a stretch parallel to the y-axis. That's a weird way of saying, really. It stretches up and down. So 1 plus 3 root x, that's my graph initially. So I've really got that. Oh, well, and it becomes 2 plus 6 root x. Now look, I think I've doubled both of it. I think I've done whatever my first graph was, 1 plus 3 root x. I've times it by 2. Look at that. 2 plus 6 root x. I've doubled both parts to get this. Can you see it's one of these? It's a number times by whatever I started with. And the number is outside the bracket. It's not inside the bracket, it's outside the bracket. So this is going to stretch it up and down. So let's draw the graphs. The red one is what I started with. This is the graph. Notice it starts at 1. Right there, it starts at 0, across 1 up. And this is the root x graph. But because it's 3 root x, and I've got a 1 plus, that's my red graph. You're not there at this stage to know that. We would get that from the computer or from a graphical calculator. Notice what the blue one looks like. It starts, well, it looks as if, to me, it starts at 3, but actually I don't think it does. Because if I put x equal to 0, and that's the, this line here has basically got x equal 0 coordinates. I think it actually starts at 2. You just can't see it properly. I think it actually does that. But because it kind of goes on the line, you can't quite see it. I think it starts at 2 anyway, so you have to take my word for it. But basically this graph then, it's a stretched version. It's like this one, but higher up. So the way we describe this, notice the wording here. It's a stretch by a scale factor of 2. 2 because of this number here. It's twice as high. Parallel to the y-axis, a posh way of saying it's stretched upwards. Next example, what have we got? Y equals f of ax. So my example here is, oh, that's gone wrong there. That should have been a 3 like that. Let's do that. My example here is y equals x cubed, and it becomes y equals 5x cubed. Now, what I want you to think about this is, my y equals x cubed graph basically does that. So I want you to think to yourself, what does making a 5x do? Now, last time a 5 in times in made a stretch, and this is also a stretch. Last time it was a stretch going upwards, but this time, because it's inside the bracket, it's going to stretch left and right. And again, bear in mind, the weird thing is that 5 times it makes it stretch, not by 5 times bigger. It does the wrong thing because it's in the bracket. A stretch of a 5th. These are the graphs. There's my x cubed graph. And this is my 5x all cubed graph. Actually, there's two ways to think of that. You could think of it being stretched up, but I'm thinking of it being stretched inwards. That has gone to that. By a scale factor of 5th. Notice that. It's not 5, it's a 5th. 2 more to do. This one's a relatively nice one. It just says, describe the transformation that y equals x squared becomes y equals minus x squared. Basically, you'll notice I've put a minus in front of it. Another way of thinking of that is times by minus 1. This is the x squared graph there. That's y equals x squared. The minus x squared just goes underneath. So whenever you just put a minus in front of the function, it's a reflection in the x-axis. Quite nice and easy. The last one's kind of alright, but it's slightly different. This is a reflection in the y-axis. Notice the minus now is inside the bracket again. So describe the function, the transformation that changes root x into the square root of minus x. Now, this is, by the way, root x. Again, it's one of those ones at the moment you wouldn't necessarily know. That's root x, and notice this is y equals the square root of minus x. And that's it. You'll notice it has reflected that way. So we just say it's a reflection of the y-axis. Now our job is to learn all of these and get practice, and we'll do some practice in class. We'll practice those initially, and then we'll do some exercises from the book. But I suppose what I want you to be aware of is there were 6 different stretches which I'm just moving back through now. 2 of them were translations. One was up down, one was left right. You need to know both. There were 2 stretches. One was a stretch up and down, one was a stretch left and right. There were 2 reflections. One was a reflection up and down, one was a reflection left and right. So we've got to get our heads around all of these. And critically, when it's left and right, it will always have something to do with brackets. When I say that, I'm not sure about the first one. Okay, so best of luck, and we'll do this in class. Okay. Thank you.